We can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang. We now know how our world ends. Our affinity with sci-fi movies and perhaps the Bible might point toward a big bad apocalypse. But what if we tell you that the end of the universe is no different from its inception? The James Webb Telescope has revealed that the universe has stopped expanding. Popular scientist Brian Cox predicted this years ago, giving us the most realistic starting point to imagine the end of the world. We can look to light that began its journey before there were galaxies, and that's the oldest light in the universe, which is, by the way, one of the pieces of evidence for those who don't believe in the Big Bang. The answer is simple: you can see it. We're heading towards Big Bang 2.0. Join us as we explore why the world has stopped expanding and James Webb's terrifying discovery. If we're certain about anything in our knowledge of the universe and its history, it's that our very epoch of existence is centralized around this event called the Big Bang. Of course, there are alternative theories that recognize the beginning of the universe, such as eternal inflation or an oscillating universe, but we're not getting into the validity of these theories today. Mainly because the astronomical community has now readily accepted that our history in this universe starts with a Big Bang, and the ideas that succeed the Big Bang are also based on the same common point of the universe's birth. While the Big Bang is a common term in the theoretical knowledge of astronomy and space, we're hardly aware of the ins and outs of the phenomenon unless you're a nerd who has spent hours watching some excellent visualization of the Big Bang. To be fair, the phenomenon was more than an explosion, or so to speak. Simply put, the Big Bang finds its origin in a single point, a point that was infinitely hot and dense that inflated to extreme lengths. All of this happened when the universe was incredibly young. Believe it or not, at the time of the Big Bang, the universe was only 10 to the power of minus 34 seconds old. That is a 100th of a billionth of a trillionth of a second in age. This is when the universe experienced an incredible burst of expansion, aka the infamous explosion or inflation. During this process, space expanded faster than the speed of light, so you wouldn't have even blinked when the universe grew 90 times in size almost instantaneously. From subatomic size to golf ball sized 1 second after the inflation, the universe began to cool, leading to the formation of matter as we know it today. So, as far as the timeline goes, within a second our universe was full of every particle we've learned about in our chemistry class, willingly or otherwise. Protons, neutrons, electrons, anti-electrons, photons, and neutrinos are the legacy of the Big Bang. Magical, right? Well, figuratively it looks like it, but our understanding of the universe's inception is highly theoretical. We've come a long, long way since the first moon landing, and since then our technological advancement has grown exponentially. Back when scientists were studying the Big Bang only based on mathematical formulas and scientific models, they wouldn't have imagined that we'd be exploring the possibility of life on Mars. There have been some big breakthroughs in our pursuits to study the universe and explore space, yet even then our existing technology is pretty limited. You see, we can't recreate the Big Bang or peer back at the event itself. Our biggest piece of evidence comes from the cosmic microwave background, which has allowed scientists to observe the echo of the Big Bang. While this mechanism is groundbreaking in the study of the universe, it's also theoretically limited. The biggest barrier in this particular methodology is the fact that we can't see the gravitational waves or the residual radiation that came from the expansion itself. So while our entire knowledge rests on theoretical tenets, scientific theories have a large room to be disproved as well. Yep, we're pretty sure about the Big Bang as a concept and how it was monumental in creating our universe, but there are some chunks of its aftermath that we've gotten wrong. As shocking as it is, theories about our universe are largely based on data that is prone to human errors all the time. At the same time, some of our data is also highly conclusive about the Big Bang. Let's just say that at this point in time, it's not easy to disprove the theory altogether. The theory is our universe still expanding. In the last decade or so, our only saving grace to study the Big Bang was the Hubble Space Telescope. Now, of course, all bets are on the excellent precision of the James Webb Space Telescope. Before we got to use these powerful technological instruments, one of the biggest points of contention in astronomical study was the expansion of the universe. If you pick some science textbooks from the early 90s or so, you'd read about how the universe is widening. In other words, the universe is expanding. That's one little scientific fact that we've held on to. But the real snafu here is that perhaps we don't understand what the expansion of the universe entails. More importantly, we got to ask ourselves if the universe is actually expanding because, spoiler alert, the James Webb Space Telescope is telling us otherwise. Lo and behold, the universe has stopped expanding. And hey, while the world is still intact, you might want to improve your internet experience safe and secure because we certainly have. This is why we're happy to reveal our very own secret to secure browsing and accessing deep-blocked content to make some hefty informative videos. Today's video is sponsored by the champion of safe and accessible internet, Atlas VPN. With more than 6 million users worldwide, Atlas is changing the game for everyone. Alright, this service won't be available in space, but Atlas would make your internet experience super secure, pure, and quick. Can't watch shows that are locked in your region? Connect to Atlas and voila, you're in. You don't have to be an expert in tech or computers to work the service. It works like a charm for anyone and everyone. That too for just $1.83 per month plus 3 extra months. So why choose Atlas? Atlas kills malware attacks, keeps your good searches secure, unlocks content from all over the world, and offers the best deals in the market. You can get all of this for all of your devices via a single subscription. Grab the big deal because now Atlas VPN Premium is just $1.83 per month plus 3 extra months, and with a 30-day money-back guarantee. Protect your privacy and get many benefits of Atlas VPN for a ridiculously low price. You can take this deal by clicking the link in the video description below. Be quick as it's a limited-time offer. So while we thank Atlas VPN for sponsoring this video, click the link in the description to avail the limited-time offer. Your internet experience just got a whole lot better. And now, before jumping into the implications of this groundbreaking shift from our universe's trajectory, let's just talk about our understanding of this perplexing phenomenon in the first place. The most common knowledge associated with a Big Bang characterizes it as an explosion, and well, fiction and popular media have put solid imagery to this process as well. Any piece of media would depict the inception of the universe as some sort of a blast that hurls tons of energy and matter in every direction. Scientifically speaking, that sort of visualization is incorrect. Despite the widespread use of the explosion and inflation of the word, the birth of the universe wasn't exactly a blast. Scientists want us to correct our understanding of the universe. In NASA's own words, the universe did not expand into space as space did not exist before the universe. Instead, it is better to think of the Big Bang as the simultaneous appearance of space everywhere in the universe. Our understanding of the phenomenon also reveals that our universe has lived through a durable cosmic period that was only disrupted by the reionization in space. Before that particular chemical conjecture, our universe was just pitch-black dark. The let there be light moment of the universe only occurred 400 million years after the Big Bang. Yep, that's right. You see, the big explosion only created the basic tenet of all living beings and heavenly bodies in the universe. For 400 million years, the universe was plunged into darkness because, well, it's simple, there were no stars or galaxies. When that was rectified, as clumps of gas turned into stars and galaxies, only then did the universe get out of its cosmic dark ages. Here's a little trivia for you guys. When do you think our solar system came into being if the universe was just darkness and eeriness for 400 million years? Well, our solar system was born 9 billion years after the Big Bang. So yeah, sorry sci-fi movies, there's a huge disconnect between the so-called explosion and scientific theory. And of course, this changes everything. The way things are, our universe still exists as a single inception point. It hasn't moved or expanded ever since the Big Bang. What really happens is that space has been stretching along with time, and it carries matter with its trajectory. To put it in clear-cut words, the universe isn't expanding the way we visualize or even understand it. It is actually the active stretching of space that precedes the expansion of the universe. We know it's a bit complicated to comprehend this, but it's also important to understand the implications of what we're about to tell you. For the purpose of this video, we continue to use the phrase expansion of the universe to signify the active movement of our space, mainly because even scientists are comfortable using the exact framing to describe the recent discovery made by the James Webb Space Telescope. As we delve deeper into the implications of the universe's sudden halt in expansion, it's crucial to consider the potential scenarios that could arise from this shift. One of the major questions that scientists are grappling with is whether the universe's cessation of expansion is a temporary phase or a sign of a more profound and lasting change. Understanding this could reshape our predictions about the universe's ultimate fate and offer new insights into the nature of cosmic forces. The concept of the universe potentially contracting back to a singular point, often referred to as the Big Crunch, is a fascinating and somewhat unsettling idea. This theory suggests that the same forces driving the universe's expansion could eventually reverse and lead to a collapse. If this were to occur, it could result in a dramatic and intense recontraction, where galaxies, stars, and all cosmic structures are drawn together. This scenario would mark a profound end to the current phase of the universe, potentially leading to a new cycle of cosmic evolution. In addition to the Big Crunch, scientists are also considering the possibility of other outcomes. For instance, the universe might reach a state of equilibrium where the forces of expansion and contraction balance out, resulting in a stable, static universe. Alternatively, it could enter a phase of Big Freeze, where the universe continues to expand but at an ever-decreasing rate until it reaches a point of near-total entropy. Each of these scenarios has different implications for the future of cosmic structures and the ultimate fate of matter and energy. Another key aspect of this discussion involves the nature of dark energy, which, as mentioned earlier, constitutes about 70% of the universe. Dark energy's role in the universe's expansion and its potential reversal is crucial to understanding these future scenarios. Recent findings from the James Webb Telescope suggest that dark energy was once a significant driver of expansion, but its effects seem to be diminishing. This shift raises questions about the fundamental properties of dark energy and whether its behavior might change further as the universe evolves. Furthermore, the study of cosmic microwave background radiation, which provides a snapshot of the universe's early state, is essential for understanding these shifts. By analyzing variations in this background radiation, scientists can infer the universe's expansion history and test models of cosmic evolution. This data helps refine our understanding of dark energy and its role in shaping the universe's future. It's also worth noting that the current understanding of cosmic expansion is not solely based on observational data but also on theoretical models. These models often rely on general relativity and quantum mechanics to predict cosmic behavior. As our observational capabilities improve, such as through advanced telescopes like James Webb, these models are continually tested and refined. This iterative process is crucial for enhancing our understanding of cosmic dynamics and addressing questions about the universe's fate. In addition to observational data and theoretical models, simulations play a significant role in studying cosmic evolution. By using sophisticated computer simulations, researchers can model different scenarios of cosmic expansion and contraction, incorporating various factors such as dark matter, dark energy, and gravity. These simulations provide valuable insights into how the universe might behave under different conditions and help predict potential outcomes. As we move forward, interdisciplinary collaboration will be essential in advancing our understanding of cosmic phenomena. Astronomers, physicists, and cosmologists must work together to integrate observations, theories, and simulations into a cohesive framework. This collaborative approach will be key to unraveling the mysteries of the universe and addressing the profound questions about its ultimate fate. Moreover, public interest and engagement in cosmic research play a crucial role in advancing science. By fostering curiosity and providing accessible information about cosmic discoveries, we can inspire future generations of scientists and contribute to a broader understanding of the universe. Educational outreach and science communication efforts help bridge the gap between complex scientific concepts and the general public, fostering a deeper appreciation for the wonders of the cosmos. In summary, the recent revelations about the universe's cessation of expansion highlight the dynamic and ever-evolving nature of cosmic research. The interplay between dark energy, observational data, theoretical models, and simulations will continue to shape our understanding of the universe's future. As scientists explore these questions, they not only seek to answer fundamental questions about cosmic evolution, but also aim to inspire curiosity and wonder about the universe's ultimate destiny.